4.5 billion years ago, the inner solar system was a crowded orbital plane defined by high-speed impacts. Into this environment came Theia, a Mars-sized protoplanet that struck the young Earth with enough force to vaporize solid rock. The energy released by the crash was so intense, it reduced the planet's surface to a global ocean of magma. The debris ejected from this collision formed an orbital ring that slowly coalesced, eventually binding together to become the Moon. Finding physical proof of this event is difficult. Because the impact liquefied the planet, and billions of years of plate tectonics have since recycled the crust, the original surface from Earth's birth has been erased. To understand our origins, researchers have to look past the rocks themselves and hunt for indestructible chemical signatures trapped deep within the planet's interior. Solving the mystery of planetary formation requires analyzing the specific isotopic ratios that serve as a permanent record of the solar system's earliest events. These records are often found in meteorites like this ordinary chondrite. Because these rocks have remained frozen since the solar nebula formed, they serve as a baseline for the chemical makeup of the early solar system. Standard models suggest that planets form in distinct stages. Dust grains clump into pebbles, which then merge into larger bodies called planetesimals. We know smaller bodies like Mars followed this path quickly, finishing their growth in as little as 1 to 5 million years. To determine if Earth followed the same schedule, geochemists use the hafnium-tungsten chronometer. By measuring these specific radioactive isotopes, researchers can date the exact moment a planet's metallic core separated from its silicate mantle. The hafnium-tungsten data shows that Earth took much longer to form than its neighbors, continuing to accrete mass for 70 to 120 million years. This delay meant Earth was still growing when the solar system reached its most unstable phase, ensuring that its final stage of development would involve a high-energy collision. When the Apollo missions returned with samples from the lunar surface, researchers were finally able to compare the chemistry of the Moon directly to that of the Earth. Laboratory analysis of these samples focused on isotopic signatures that typically vary from one planet to another. If the Moon was formed from the remains of the impactor, Theia, it should be composed of material that is chemically distinct from Earth. However, the isotopes for oxygen and titanium in these samples match Earth's mantle nearly identically. This finding contradicts the standard model, which predicted the Moon would look like an alien world. One explanation for this similarity is the synestia theory. It suggests the impact was so violent that it vaporized both bodies into a single shared cloud of rock vapor, allowing the materials to thoroughly mix before the Moon condensed. In this scenario, the giant impact was not just a collision, but a total homogenization of two worlds that created the shared chemical identity we see today. Traces of this process are still appearing in the modern landscape. In Greenland, the ancient rocks of the Isua supercrustal belt offer a glimpse into the cooling of that original magma ocean. These formations contain specific iron and tungsten anomalies that distinguish them from any modern volcanic rock. These anomalies are signatures of primeval crystals that formed and settled out of the liquid rock as the magma ocean solidified. Being denser, they sank to the bottom of the mantle, remaining undisturbed at the core mantle boundary for billions of years. Over geologic time, mantle convection pulled a portion of this ancient reservoir back to the surface, incorporating it into the magmas that formed Greenland. These ancient signatures demonstrate that the high-energy events of Earth's formation are still preserved in the planet's interior, providing a permanent chemical record